when you end up with, the worksheet is also online, but if you want a hard copy, I'll come by and give you one. I checked with the office. If you haven't, you don't have to go right now, but if you're coming in on your off day, make sure you sign in the office and then sign out when you leave. Some of you are probably going to do that anyway, but sign in when you come in, sign out when you leave. I think the first thing may be for you to, somebody come on your off day. I think this is really going to help. So, I mean, if I felt like I could get everything done, just in like 2 days a week, I would, but it's not looking good. So, thank you. Okay. This is the homework. The bell work over there. Oh. The bell work over there, those should be able to answer those pretty quickly. This is just a hard copy of the homework. I mean, it's on campus. Some of you like writing on your, some of you like writing on your, you want to do it like on a PDF and turn it in, that's perfectly fine. I have no problem with that. This is going to be for notes today. This will be for notes today. Oh, you. There we go. How's your ankle?
It's okay.
Okay.
Oh, I already have one.
Okay. Are you one? All right. So, first one up here. V of t is the velocity of a car. How far did it drive? Anybody? Shout it out. 180 miles? 30 miles per hour times 6 hours, 180 miles, right? Easy enough? Here's calculus. Ready? What's the area of this rectangle? 180, right? Area of this rectangle is 30 miles per hour times 6 hours. Hang on. Miles per hour times 6 hours. 180 miles. Congratulations, you're doing calculus. Here, you just answered the following question without realizing it. There. Aren't you smart? Integrals ask you to find the area under the curve. They ask you to find the area under the curve. This is saying the velocity times the change in velocity. Sorry, times change in time. Velocity times the change in time equals how far we went, right? We're going to call it displacement. Okay. B. What you got? $220? I really don't know. I made a problem. I didn't answer it yet. 220? Okay. How'd you do that? You made two rectangles. 30 times 4, 50 times 2. For this one, 0 to 6 hours, 220 miles. Great. How about the bottom one? 240? Yes, no? How'd you get that? Okay. Does anybody know what shape this is? It's a trapezoid. It's a weird looking trapezoid, but it's a trapezoid. It's a right trapezoid. Those are right angles, aren't they? This is a right trapezoid. Does anybody know the area formula for a trapezoid? I will give you a hint. It's right over there. You see it?
Yeah.
What is it?
1/2 of base 1 plus base 2 times 2.
This is a trapezoid. Okay, what is base 1 on this thing? That's the 30, yes. Base 2 is 50. 30 plus 50. And then the height is 6. The change from here to here, right? Okay. Now you said it averaged 40, right? Hey, look. 30 plus 50 divided by 2 is 40. So yeah. So 240, you said? Congratulations, you're doing calculus, you're doing integrals. Integrals find the area under a curve. Okay? Integrals find the area under the curve. Sometimes these are nice, easy formulas, like rectangles, trapezoids, and up here, we've got a quarter of a circle, right? Okay. Please note the one thing that this does not do. This says 180 miles, right? Does that mean we're at mile marker 180? No. What does 180 miles mean? It's how far we've gone. It's our displacement. It doesn't tell us where we are. Because for that, you need to know the starting point, right? You need to know the starting point. And yesterday, we learned that the starting point is the plus c. Okay? This does not have the plus c, does it? Okay? This just tells you how far we've gone. It's the net change, the displacement. How much something's changed over time. Okay. Now, I want you to try the area under a curve up there. This one right here. Try this one on your own, please.
Does it stop at -2 or -3?
-3.
Okay.
Did I give you a sheet for notes?
Oh, it's
Yeah, same thing. All right, let's see here. So area this first part's going to be pi r squared divided by 4, right? What's our radius on this? That's 4, right? Okay. So that's this. And then we got, what did you do down here? Did you do a triangle or a rectangle, or did you do a trapezoid? Either one works, I'm just asking. Trapezoid? Okay. Okay. So if we do a trapezoid, what's the, let's see, so we do 1/2 base 1. In this case, base 1 is going to be this way, isn't it? 1, 2, 3, 4. Base 2, 1, 2, right? Times the height. What's the height of this? It's -3, isn't it? You're going to say, Mr. Kuhne, you can't have negative area. You're correct. We can't have negative area. But if we pause and go back a second, we think about this in terms of velocity. This was velocity. I was going forward. I was slowing down, and then I stopped, right? Pause for a second. I had 0 velocity, so I wasn't moving, and then I was moving backward, right? So this isn't telling us how far we went. It's going to tell us how far we were from where we started, our displacement. So yes, we can have negative area. Okay, so -3. All right, so 4 pi, and then -9, right? Okay, someone whip out a calculator, help me out here. It's like 12 something, but
12.56, I think.
12.5, well, calculus, we need 3 places beyond the decimal.
12.563, I think. 12.562.
All right, let's see.
No, it's not.
4 times pi -9. So if we do this all together, it's going to be 3.566. And you can have extra decimals, 3, 7, 0, 6, blah, blah, blah. Okay. So integrals find the area under the curve. Okay. So far, we like it when there's nice, cute, easy geometric formulas, right? Over there it was rectangles and a trapezoid. Here it was a circle and a trapezoid, or a circle and a triangle and a rectangle. We like those. But what happens when it's not cute, sexy shapes? What if this is the only information you have? Here's x, here's x, here's f. How do I find the area under f from 0 to 6? Before we get into we'll talk about the theory of this probably a little bit tomorrow and what we're doing, but here's a basic idea. Sometimes you can't find the answer exactly. This may be what the curve looks like, but I don't know exactly where all the stuff is in between. Okay? If they give us an equation, we can probably do it, and we will get to that. But for right now, this is the best we got. This is the best we got. So what do? How do we find the area under this? Yes. We're just going to approximate, yeah. What shapes do you think would fit under this nicely? There's not really a good shape, is there? So mathematicians sometimes like, okay, let's make the best possible fit. Maybe not the best possible fit. Instead of the best possible fit, let's just take an easy things that we know how to do. We're going to start with rectangles. We know how to find rectangles. That's easy, isn't it? Okay. So once upon a time, there was a mathematician named Riemann. He was German, and that's all about all I know about him. Okay. That's the end of your history lesson. Well, he gets credit for this. Left Riemann sum is basically just telling you left rectangles. Okay? We're going to make rectangles starting on the left side. Okay? So, go ahead and set your pencils down for a moment. I'm just going to draw this, and I want you to be able to like watch and just think and process, okay? And then tell me like what's good, what's bad about this, okay? What do you like, what do you not like? Okay. So these are called partitions or subintervals, okay? I've got a big interval from 0 to 6. These partitions or these subintervals, it's just where we're cutting it up, okay? I'm going to cut it up from 0 to 2, 2 to 4, 4 to 5, and 5 to 6, because those are the numbers we have. Okay? All right. We're going to approximate this by doing this. We're going to start on the left side of each box. Left side of this box, and I go straight over. Left side of this box, whoop, go straight over. Left side of this box, whoop, go straight over. Left side of this box, straight over. Okay? So what's the area of this box? Just shout it out. 6, 3 times 2, right? It's 3 times 2. How do we get that? We did f of 0, that's the 3, times the width of the box, which is the 2. The delta x. Still with me? Area of this box. Well, let's see here. The width of the box is still 2, right? The height of the box is 7. 7 times 2. F of 2 plus the times the change in x. All right, how wide is this box? 1, it's a lot smaller, isn't it? Okay. Change in x, we're using f of 4 now. That was 9 times 1. Then we're going to have f of 5. Change in this box, change in x. We get 4 times, again, 1. Okay. So we're going to get 6 plus 14 is 20, 29, 33. Just taking a look at that, how do you feel about that area? Good, bad, okay? How are you feeling? What bothers you about it or doesn't bother you about it? Come on, talk to me, please. Yeah. If it were only going up the whole time, it would always be under, wouldn't it? Okay. But there's a lot of gaps in there, isn't there? Okay. If you need a copy, if you want to write this down now, go ahead. You can write it down. Okay. That is left Riemann sums. Guess what right Riemann sums are? You start on the right side. We're going to start on the right side. Now, I've had some people that I've had some people that say, okay, start on the right side of this box and just go over, go over, go over, go over. That's fine. I had one student that said, oh, no, you just start on this side and do it this way. Just do it backwards. I thought that was pretty good too. It gets the same thing. But sometimes it's easier just to start from the right side and go backwards. So I'm showing you that, but it's the same thing. Of the two numbers on this interval, I'm just going to start on the right side and go over. Start on the right side and go over. Start on the right side. Start on the right side. Okay? And then we're just going to do the same thing, though. We're going to find the area. You do need to know the difference between right Riemann sums and left Riemann sums. Okay? If you do left Riemann sums and they want you to do right Riemann sums, you get it wrong. I actually don't know if that's going to change anything on this problem or not. It's going to change the answer. It might, I don't know. Yes, we will do that. We will do that. In fact, we'll do that next for you, okay? Just because you asked. Okay, so this time I'm using f of 2. Now the change in the width of the box is still delta x. But this one starts at 7, right? 7 times 2, f of 4. 9 times 2, f of 5. And we got, let's see here, 4 times 1, and then 1 times 1. All right, so let's see here, 14 plus 18, 32, 36, 37, is my math right? You'd think I'd be able to add in my head being a calculus teacher, but my wife doesn't let me balance the checkbook, so. 37. Okay. That's a pretty sizable difference, right? If you think about this like in terms of miles, like, oh yeah, how far did the car go? Well, it went 30, either went 33 miles or it went 37 miles. That's a big difference. Abby, okay? I get it, I get it. Post lunch, all day, I get it, it's cool. All right, so he just said, hey, why don't we average them? Why don't we average them? That's a good plan. And you know what averaging them would look like? It would look like this. What shapes are those? Trapezoids. We're going to do trapezoids next. Sorry, we just did Riemann sums. Now we're going to do trapezoids. But yes, so there's two different ways to do trapezoids. First way is do the left, do the right, and then average them. Okay? Yes, you can absolutely take the left sum plus right sum, divide by 2, that is trapezoid. That's perfectly legit. Okay? Totally cool with that. The other way is just to make trapezoids again and again and again. So I make a trapezoid. So it's going to be 1/2 base 1 is 3 plus base 2, which was 7, times the height, which was 2. Then 1/2 base 1, which is 7, base 2, which is 9, times the width, which is 2. 1/2 base 1, base 2, times the width. So let's see here. 2.5, 6.5, 16, 10. $35? We have those up? I think it's 35. Should be 35. 35. Okay. That's trapezoids. Now that's better, but that's still, if you look at this, yeah, we're a little over there, a little under there, a lot under there. That's pretty close. It's hard to tell, isn't it? Okay. The big question is going to be, how can we make this more accurate? Well, if this is all the information we have, that's it. Okay. But if you've got an actual function, if you've got an actual equation, how are we going to make this more accurate? We're going to shove more in there. We're going to make lots and lots and lots of rectangles. Like a stupid number of rectangles, like an infinite number of rectangles. We're going to shove them all in there. Yes? Yes. Left side to right side, just connect the two sides. You're welcome. Trapezoid is normally the best way we can go. Okay? Most of the time. There's something called Simpson's rule. There's no talk about that. We won't get into that. But for our purposes, trapezoid is normally the best way we can go. That's pretty good. That's pretty good. If I told you estimate the area under this curve, like, okay, it's a little over there, under here, that's pretty good, right? I feel pretty strongly that that's a good estimate. Okay, and then the last one is midpoint. Midpoint, not used as often, okay? In terms of importance, I would say 1. I would call this 2 only because this kind of uses these. And I would put this I would rank this 5. Not 500, but 5, okay? Top 5 all time, yeah, but just not used as often, okay? Will it still come up in the AP exam? Probably. They'll probably throw 1 on there like that, okay? But normally we just do left, right, or better yet, trapezoids. Okay? I'm going to show you midpoint. The idea is do the midpoint of the interval. Well, we don't have the midpoint of this interval, do we? I don't know what that number is. So this one, I'm actually going to say midpoint using 2 subintervals. Because I'm actually going to do it from the midpoint is right there, isn't it? 2 is the midpoint of 0 and 4. And we can say 5 is the midpoint of 4 and 6, right? Okay, so that midpoint right there. And we just make boxes again. Just make boxes. Okay? So, what does that look like? It looks like, I'm going to use a different color here. Use green. It looks like this. Do you see what's going on there? Yes.
So the top of the box is just the highest point in between those intervals.
Yeah.
Okay.
And you can see why midpoints sometimes can be, If we do it this way, we're leaving out, we're not making as many boxes, are we? Not making as many partitions. Okay? So that's kind of why I don't like midpoint. It's still a valid way, it's just, it's not my favorite. So if we do midpoint here, okay, what's the height of the box? 7. So f of 2 times the width of the box. So it's 7 times, how wide is that first box? 4, isn't it? 4 minus 0 is 4. Plus, okay, this one right here, it's the f of 5, isn't it? F of 5 times the width of that box. So that's 4. And the width of that box was 2, right? I'm going to put some numbers under here. We got this from 4 minus 0. And we got the 2 here from 6 minus 4. Showing you where those come from. This is the delta x. Okay. And so we get, let's see here, 28 plus 6, 34, right? Not bad. So these are some ways that we find the area of the curve. Now remember I told you, like, calculus, we want you to be able to do it graphically using a table and using equations, right? We've done table. If I just look at the table, I can do this. I would me personally, I would probably make a graph because I like pictures. But if you could just figure it out from here, that's cool. Sometimes people can figure out, look at this in their mind and build a graph in their mind. That's fine. Okay? Done graphically. Done graphically here. Okay? Done graphically over there. What's going to come next is how to do it with equations. Okay? That's going to be coming on Monday. All right? And at some point, I'll be showing you how to do this with Excel, because if I give you data in Excel, you can find the area under curves using, because you can tell Excel, here, do length times width for these numbers, right? We'll do that too. But that's still discrete. But we'll get there. I don't know when. Curse you, COVID. But we'll get there. All right, I need 2 questions before we wrap up. Yes?
My question for this might be already implied. So do you ever use just the left and just the right, or do you always have?
So it depends on the problem. Normally, you end up averaging them. If you're talking about like real life applications, we're normally going to end up averaging them. Okay. Oftentimes, for like lots of equipment, it's not going to make that big of a difference, because if you think of like the veneer equipment, like if I'm taking data every 1/100th of a second, there's not going to be that big of a difference normally. So it's not going to be a huge difference between the two. But yes, it normally makes more sense in applications. Let's just add left, right, average them, or just say, let's do midpoints, because that's the same thing. Good question. Yes.
You mentioned there probably would be a question to use midpoint. So how would that work? Would it say would it tell us when you have to use midpoint, or would
yes?
Okay.
Yeah. So if these happen, they're not going to say, here, find the area, and then give you the left answer, the right answer, the midpoint, and the trapezoid, and hope you guess the right one. No, they're going to tell you, approximate the area under this curve using midpoints with 2 subintervals, or using left Riemann sums. They will tell you. Okay? That's a good question. Yes. Yes.
So we saw for the area under, like the quarter circle, then you went up for the trapezoid, right? Like you went up the last line, like you would imagine going up.
Okay.
It's like, why didn't we use the trapezoid under it as well? I guess.
Okay. When we say under the curve, that's a good question. When we say under the curve, you think, oh, why am I not going under this way, right? Because if I go under this, it keeps going forever. When we say under the curve, we mean between the curve and the x-axis. Area under the curve is area between the curve and the x-axis. But that's too long, so we say area under the curve. Bye, everyone. I will see many of you tomorrow. And I'm going to, again, this recording is going to be on campus. If you can't come in tomorrow, join the Google Meet or try to do that for tomorrow. Yes. You don't get it all done. It's cool, but work on it. Okay. Yes. 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 There will be a Google Meet.